morning. We're going to talk about coordinates, in particular spherical coordinates and Cartesian coordinates, and how they're related to each other. So the coordinate axes, as you know, have x, y, z. Put my coffee down. Z, y, and x coming out of the board. And then we're going to also assign spherical coordinates to a point. So let's imagine we have a point starting from the origin O, going all out to here, and we'll call this vector xi with coordinates x, y, z. So xi is a vector that goes from the origin to some point, and its coordinates are x, y, and z. And now we also want to describe that same point using spherical coordinates. And for that we'll use the radius, the latitude, and the longitude. So for the latitude, we imagine cutting a plane that's parallel to the x and y axis. So we have this plane along here, the x and y axis, and then relative to that, we measure the angle up to the vector xi, and we'll call that phi, and phi is the latitude. So phi is the latitude, and phi is going to vary from pointing straight down. So if we bring our vector all the way down here, that will correspond to phi equals minus pi by 2, which is the south pole, and then all the way back up to the top, which is phi equals pi by 2, which is the north pole. So phi is going to be between minus pi by 2 to pi by 2. Remember, phi is latitude. All right. Also, we'll have the radius, which is going to start from the origin and move radially outward along the vector xi. So out in this direction, we'll have r hat, which is a unit vector pointing in direction. I forgot to write down xi, so it's a unit vector pointing in the direction of increasing latitude, phi unit vector. And then the last one is going to be the longitude. And for this, we will have a plane which cuts through the vector z and r. So that plane, and then we look at the angle that makes with the x-axis. So along this way, we call this lambda, which is the longitude. So I forgot to write down r is the radius, and r is going to be between 0, which is at the origin, all the way out to potentially infinity. And finally, the last one is lambda, which is the longitude. And this one, lambda, can go fully around 360 degrees. So we can start at x, go all the way around, and come back to x. So lambda is going to be between 0 and 2 pi. All right, so these are our spherical coordinates. Now we want to relate them to the Cartesian coordinates. So for this, let's start off with phi, right? So if we take that plane that cuts through xi and r, then we're going to have xi and r. Yeah, so we'll have a picture like this. So this is a picture of that plane. This is the z-axis, and the r vector, or sorry, not r, xi, the xi vector. And then this is going to be the perpendicular to xi. So it's this line here. And this angle, of course, is the latitude, which is phi. So if we drop a perpendicular from this point downwards onto the plane spanned by x and y, then we'll get this point out here. And this length over here is going to be the length of xi. So xi times the cosine of the angle phi. So we know it's the cosine because if the phi is equal to 0, this is going to be a finite length. On the other hand, if we go all the way up to phi equals pi by 2, the length along here is going to be 0, and so that's a sine of pi by 2. Sorry, cosine of pi by 2 is 0, not sine. And then the other distance is from here to here, which will be our z-coordinate, right? So this z-coordinate, z, right, coordinate, is going to be the length of xi times the sine of phi, right? Because this length goes to 0 as phi goes to 0, and sine of 0 is 0. So we found what the z-coordinate is of our point C. So we found this coordinate now. We also want to find the x and the y coordinate. And for that, we will look at the xy plane. So if I put a picture of the xy plane, y and x, right? And this vector here is going to be along this way, right? And the length of that vector is going to be this length over here, right? C cos theta. So this length is C cosine, sorry, not theta, phi. And this point here is this point over here. And then we can use some trigonometry, right, to find out what this length is. So it's going to be this length times the cosine of this angle. Remember, this is lambda, right? This angle is this one. So this will be C cosine phi. And then when lambda is 0, so it should be cosine lambda, the longitude. And then this length over here, this, by the way, is the x coordinate. And we can do the same thing along here to get the y coordinate. So the y is going to be C cosine phi times the sine of lambda, of the longitude. I hope you can see that on the edge. All right, so now we have both our z coordinate, our x coordinate, and our y coordinate. So let me write them down. So x, remember, is C cosine phi cosine lambda. Y is C cosine phi sine lambda. And finally, z is C sine phi. All right, so this is how we can relate the spherical coordinates to the Cartesian coordinates. All right, so we just express the Cartesian coordinates in terms of the spherical coordinates, and now we want to define what these unit vectors are. These lambda, r hat, and phi hat unit vectors are. In Cartesian coordinates, the unit vectors are x hat, z hat, and y hat, and these are simple because they always point in the same direction regardless of which point in space you're thinking about. But that's not the case for the spherical coordinates. For the spherical coordinates, the vectors, the unit vectors, are going to change directions depending on which point in space you're considering. So let's find out what these unit vectors are. So the way we define the unit vectors in an arbitrary coordinate system is we imagine holding all but one of the coordinates fixed. And then we take the derivative. So we find out what happens if we increment one coordinate holding the other ones fixed by a small amount. And those will define our unit vectors. So for example, if I want to find the phi hat unit vector, right, it's going to be phi hat vector is going to be equal to the derivative of the c vector, so the derivative of this vector with respect to phi. So that would be a vector which is in this direction of increasing phi, right? And this derivative is done holding the other two coordinates fixed. So lambda and r are held fixed. Now, this vector is not necessarily going to have unit length, right? You can just see right away, in fact, that the vector has, depending on how big c is or how small phi is, we're going to have different lengths. So we are going to have to put in a constant out front to make sure that it's properly normalized that as unit length. Now let's compute what first dc dphi is, and then we'll find out what c is. And then we can see if it makes sense. All right, so dc dphi, we know c. Over here, it's r cos phi cos lambda, r cos phi sine lambda, and r sine phi. Those are the coordinates. So this calculation here, if I take the phi derivative of the first term, I get r sine phi with a minus times cosine of lambda. For the second coordinate, I'll get r sine phi with a minus sine lambda. So minus r sine phi sine lambda. And finally, the last one will just be r cos phi. And we still don't know what the c coordinate acts, but what we know is that we want phi hat to have unit length. So if I compute the length of phi hat, so I do phi hat dotted with itself, I want that to equal to 1. Equal to 1. This is what I want. And we're going to pick c so that this is the case. So if I compute the dot product, I'll get c squared times this squared will become r squared sine phi squared cosine squared lambda plus r squared sine squared phi sine squared lambda plus r squared cos squared phi. And then we can simplify, so what we get is c squared times r squared times sine squared phi, and this is a common factor to those two, times cos squared lambda plus sine squared lambda plus the last term, r squared cos squared phi, oops, plus c squared r squared. C squared. All right, and then cos squared lambda plus sine squared lambda, that's equal to 1. Great. And then also here, sine squared phi plus cos squared phi is also equal to 1. So the whole thing is equal to c squared r squared. And if we want this to be equal to 1, we can solve for c. C has to be equal to plus or minus r, so we're going to pick c equal to r. So we choose c equals to r. And that means that the unit vector is going to be 1 over r, dx dphi. All right, so phi hat is equal to 1 over r dx dphi. And we can do the same thing for lambda hat. Lambda hat is going to be some constant, which we have to determine, times dx d lambda, right? So dx d lambda is going to be some constant, which I need to determine, times cos phi sine lambda with a minus and an r. So oops, put it nicely. Minus r cos phi sine lambda. And then the second derivative, sorry, not the second, the derivative of the second component will be plus r cosine phi cosine lambda. And the last one will just be 0, it doesn't depend on lambda. And now to find out what lambda hat is, we want lambda hat dot with lambda hat equal to 1. This is what we want. And we're going to choose c to make this the case. So let's compute what lambda hat dot lambda hat is. That's equal to c squared times r squared cos squared phi sine squared lambda plus r squared cos squared phi cos squared lambda. Oops. Plus r squared sine, oh, sorry, that's 0. That's good. That's 0. And let me check that I did this right. Yes. And so then this is equal to c squared times r squared. And here I have cos squared phi is a common factor, cos squared phi, sine squared plus cos squared lambda, sine squared lambda plus cos squared lambda. That's just equal to 1. So this is equal to c squared r squared cos squared phi. And if we want the whole thing to be equal to 1, we choose c to be r cos phi. And so now we know what lambda hat is. Lambda hat is going to be 1 over, sorry, it should be 1 over that, right? I want it to, if I pick c equal to 1 over r cos phi, and I'm going to get the right answer, r cos phi dx vector d lambda. And finally we can do the last one, r hat. R hat, oops, wrong vector. R hat is equal to some constant c times dx times dr, and that will be simply c times cos square cos phi sine, sorry, cos phi cos lambda, cos phi sine lambda, sine phi. And if we wanted to have unit vector, we want r hat dot with r hat to be equal to c squared, sorry, to be equal to 1. And that's equal to, in this case, we just compute r hat dot r hat, we get c squared times cos squared phi times sine cos, sorry, times cos phi, cos, sorry, times cos lambda squared plus sine squared lambda plus sine squared lambda. And cos squared plus sine squared lambda is 1. We're left with cos squared phi plus sine squared phi, which is also 1. So this is equal to c squared. So in this case, we just choose c equals to 1. So that's easy in this case. So this becomes the c hat vector. All right, so this these choices here of 1 over r for phi hat and 1 over r cos phi for lambda hat and 1 over here, these scaling factors will ensure that all the three vectors are in fact unit vectors, that they have unit length. But it also turns out that these vectors are also orthogonal, so they're not just normalized, but they're orthonormal, and so they have 90 degrees with each other. And this is something we can check right now. So, for example, let's check phi hat dotted with lambda hat, right? So that is going to be phi hat, right? Phi hat was d c d phi divided by 1 over r. So that is going to be minus sine phi cosine lambda. This one sine phi sine lambda and cosine phi. So this is phi hat dotted with, then the lambda hat. Lambda hat is going to be cosine, minus sine lambda, cosine lambda, and 0. So this vector here, this one here, remember, this is phi hat, and this vector is lambda hat. Now let's multiply the terms and add. Let's do the dot product. So I get minus sine phi cosine lambda sine lambda, minus minus makes it a plus, plus the second term, plus sine phi sine lambda cosine lambda, and the sine phi is a common factor, the cosine lambda is a common factor, and the sine lambda is a constant factor. Plus and plus makes it plus is equal to 2. It doesn't work. I screwed up. Where did I mess up? Over here. Right? This should have been a minus. And then the whole thing is 0. So it checks out that it is in fact not only normalized but also orthogonal. And for homework you can check that it's also true that phi hat dotted with r hat is 0 and lambda hat dotted with r hat is also 0. All right, so that concludes the unit vector bit. Oh, no, it does not conclude the unit vector. One more bit. I wanted to point out that these scaling factors, you can also see them geometrically that they are in fact correct, right? And that actually turns out to be much more useful when we're dealing in oceanography, and we're always working in, very often we're working in spherical coordinates if we're thinking of large scales in the ocean. And so what we're going to do is point out or motivate why those are the correct scaling factors. So if I imagine picking the xi vector, which is, the c vector, which is along this plane with the z and the xi axis, so something like this. We have the z axis of the xi vector, and this is the angle phi, the latitude, right? And so this, if I vary phi, I'm going to trace out this half circle over here, right? The half circle, and the circumference of the circle is 2 pi r, so it's going to be, the circumference of that circle will be 2 pi times the length of xi, which is just r in this case. So that's, this length here is r from here to here, right? Remember, this is the vector, we use r for its length. So if I do a small increment d phi, right, so I go from here to here, so this angle is d phi, this angle over here, and this length, right, is d xi. So d xi, that length over here, or it's the length of the vector d xi, is going to be equal to d phi times the radius, which is just r. So if I compute phi hat is going to be equal to d xi vector divided by d phi and r, right? And that's going to make sure that this is a unit length, because this length here is d xi, That's the change in c in going from here to here, right? This here is dc, this length. And it's also can be thought of, the length of that is just happens to be r d phi. So the length of dc is equal to r d phi, and therefore it has unit length. And that's why we get the r coordinate component on the bottom over here. And we could do the same thing for this component. We can rationalize where we get the r cosine phi in the numerator. So let's do that one. Now this time we're going to look down along the z-axis, and we're going to have the xy plane. So this is y, and this is x. And now we're going to draw this circle over here, right? This circle. And this is going to be where c ends up pointing out. So the length of that one, the length of this radius along here, right? This length is just going to be the length of xi, which is r, times the cosine of the angle phi. So this is r cosine of phi. That's the radius. And now if we do a d lambda, if we imagine this is lambda, and we increment by a little bit, d lambda, this angle is d lambda, and we're going to get a small vector in this direction, right, dc, dc. So the length of dc is going to be equal to that angle, d lambda, times the radius, and the radius is r cos phi, right, the radius. This radius here is going to be this length times the cosine of that angle. And so if we do again, lambda hat is equal to dc divided by its length, which is d lambda r cos phi, we get r cos phi d lambda. And that is indeed what we have up here, right? We just divide. And that you can see it's properly normalized because the length of dc is r cos phi d lambda. So we're dividing by the same length. And that's another way to view that these are in fact the correct scaling factor. All right, so this concludes the first part of the lecture on spherical coordinates. Have a good day.